You and I have always wanted the same impossible thing. We want the universe to notice that we were here. We build stone circles and cathedrals. We name mountains and craters after kings and scientists. We tell ourselves that if we can just discover something important enough, then our name might be written into the sky and never erased. In the 19th century, a quiet mathematician very nearly did that, twice. The first time the universe rewarded him. The second time it exposed just how dangerous our hunger for glory can be. And it all began with a planet that was misbehaving. In the early 1800s, astronomy was a very polite revolution. Telescopes were getting better. Star charts were becoming more precise. For the first time in history, people could track the planets with enough accuracy that tiny mismatches between prediction and reality started to matter. If the heavens really followed the rules of Isaac Newton, then every planet should move along a path that could be written down with cold confidence. If something did not line up, maybe the universe was whispering about something new hiding just out of sight. One of the people listening was a French mathematician called Urbain Le Verrier. He was not a heroic explorer with frost on his beard and a telescope on a mountain. He was a theorist surrounded by paper and ink. He took the known positions of Uranus and tried to predict its orbit using Newton's law of gravity. Something was off. The planet was not quite where it was supposed to be. Most people would have shrugged and blamed bad data. Le Verrier did the opposite. If the equations were sound and the observations were careful, then something unseen had to be tugging on Uranus, and that meant there was probably another planet out there. The idea of a hidden world was thrilling. At that point, the solar system had only 7 known planets, and each new one had rewritten human history. Already there were whispers that the pattern of the planets seemed too imperfect. Could there be something else beyond Uranus? Le Verrier was not the only one thinking that way. In Germany, another mathematician, John Couch Adams, was working on a similar problem. But Le Verrier moved quickly and ruthlessly. He used the small deviations in Uranus orbit to calculate where the invisible planet had to be on a particular night in 1846. And he sent a letter to an observatory in Berlin. There, a young astronomer called Johann Galle opened the letter and pointed his telescope at the coordinates. Almost immediately, he spotted a pale blue disk, almost exactly where the math said it should be. That ghostly dot was a new world, Neptune. No one had ever seen a planet discovered like this before. It was not stumbled upon by accident. It was summoned out of the darkness by equations alone. Overnight, Le Verrier became a celebrity. The man who had used pure thought to reach out across billions of kilometers and touch a planet. If you were him, how would you not start to wonder what else your mind could drag out of the void? Fame is a strange force. It pulls on people the way gravity pulls on planets. Once journalists and fellow scientists began celebrating Le Verrier as the man who could predict worlds, it became very hard for anyone, including Le Verrier himself, to imagine him being wrong. The discovery of Neptune seemed to say something flattering about human beings in general. It suggested that we could sit here on a small rocky world and, with enough patience and algebra, command the sky to reveal its secrets. If that worked once, why not again? Why not solve another cosmic puzzle the same way and carve your name even deeper into history? Conveniently for Le Verrier, the solar system still had a problem child. Down near the Sun, Mercury refused to behave perfectly. Astronomers had spent decades measuring its orbit, and every time they tried to fit those measurements into Newton's perfect clockwork, there was a tiny leftover. The point of closest approach, the place where Mercury swings nearest to the Sun, seemed to drift more than it should. It was only a small difference, a few dozen arc-seconds of rotation over a century, but the mismatch was stubborn. No amount of tweaking the known planets seemed to erase it. If Neptune had been found by blaming such misbehaviour on an unseen neighbour, why not do the same here? So Le Verrier did what had worked before. He imagined a new planet, tucked even closer to the Sun than Mercury, whose gravity could nudge Mercury just enough to account for the strange drift. This hypothetical world already had a name waiting for it: Vulcan, after the ancient Roman god of fire and metal. It was the perfect symbol. A searing hot planet hammering its way around the sun, just where the mathematics demanded. All that was left was to actually see it. That turned out to be harder than calculating Neptune. Watching something that orbits inside Mercury's path means staring almost directly into the glare of the sun. You cannot just sweep the sky at night and hope to get lucky. The best opportunities are during a solar eclipse, when the moon blocks the sun and any tiny dark dot passing in front might betray itself. Even then, it is like trying to see a gnat crawl across a searchlight. Still, once Leverrier announced that Vulcan ought to exist, telescopes began hunting. Human beings are very good at finding what they are told to look for. In the 1600s, a German observer, Christoph Scheiner, had already reported seeing a tiny dark spot crossing the face of the sun that he thought might be a planet. Later, it turned out he had probably seen a sunspot. Those are transient blemishes on the solar surface that can easily mimic a silhouette. But that old report now looked newly interesting. If Vulcan really was there, perhaps people had been glimpsing it for centuries without realizing. Then, in the 1840s, came the sighting that lit the fuse. A country doctor and amateur astronomer named Edmond Lescarbot wrote to Leverrier to report that he had seen a small black dot pass across the sun near its edge on a December day. He had recorded the time and position as best he could with his modest equipment. To someone already convinced that a planet must be there, this was gold. Leverrier visited the doctor in person, questioned him at length, checked his notes, and came away satisfied. He announced that Vulcan had been seen, that its orbit could be determined, and that it was time for astronomers everywhere to confirm it. And confirm it they did, at least on paper. In the following years, various observers claimed to glimpse tiny dark points near the sun, especially during eclipses. 2 French astronomers separately reported seeing a small body at the same place in the sky during an eclipse, which sounded extremely convincing. Newspapers loved the story. A new planet inside Mercury. The solar system was once again expanding, and Leverrier, already famous for Neptune, now seemed on the verge of a second triumph. The temptation to believe was enormous. Saying you had seen Vulcan became a ticket to professional attention and social standing. But there was a problem lurking behind all the excitement. None of these sightings really agreed with each other. The times, the positions, even the supposed size of the object wandered all over the place. Worse, when astronomers deliberately pointed their best instruments at the spot where Vulcan was supposed to show up next, nothing appeared. Eclipse after eclipse, careful observers reported a blank, empty sky where the predictions insisted a planet would march across the sun. Slowly, an uncomfortable possibility crept in. Maybe Vulcan did not exist. Maybe people were mistaking sunspots, small asteroids, and simple optical glitches for a world they desperately wanted to be real. If that was true, it raised an even more awkward question. What about the original mystery? Mercury still was not moving exactly as Newton's theory demanded. Something still had to explain the extra drift in its orbit. For a while, defenders of Vulcan tried to rescue the idea by proposing several small bodies instead of one planet, or belts of debris, or other patched-up solutions. Almost anything was preferable to admitting that the neat trick that had worked with Neptune might have misled them this time. The danger of success is that it trains your brain to reuse the same pattern, even when the universe is quietly telling you that this situation is different. At this point, you and I might be tempted to judge those 19th century astronomers. How could they cling to a planet that stubbornly refused to show up? How could they publish confident claims based on such slippery data? Then we notice the comment sections under modern science videos, full of people absolutely certain about theories they barely understand, and the story starts to feel uncomfortably familiar. When an idea flatters us, or when it promises to put our name in textbooks, we do not let go easily. We defend it. We massage the evidence. We see patterns where there are only smudges. The Mercury puzzle could have been a warning that something was wrong with our picture of gravity itself. Instead, for decades, many people treated it as a bookkeeping issue that just needed one more unseen object added to the ledger. Yet there were a few astronomers who kept careful track of the numbers and quietly worried. No configuration of hidden planets they tried could quite reproduce Mercury's motion without causing chaos elsewhere in the solar system. They did not have an alternative theory to offer. All they had were questions and a growing feeling that perhaps Newton's beautiful framework was being stretched beyond what it could bear. If you have ever had a moment where your favourite explanation stops working, you know exactly how tense this period must have felt. Imagine being one of those scientists, watching the data drift away from the model you were taught to revere as almost perfect. Do you double down and insist the missing pieces will eventually be found? Do you throw out a theory that has explained almost everything for 2 centuries just because of a tiny mismatch in one planet's orbit? Or do you sit in that uncomfortable in-between space and wait for something radically new to arrive? History tends to remember only the final answer. We celebrate the breakthrough and quietly forget the long years when people were stuck between loyalty to the old and suspicion that something new was needed. The story of Neptune and Vulcan is a rare chance to watch that tension play out in real time. On one side is the triumph of a method that finds a planet by pure thought. On the other is the embarrassment of chasing a mirage because that same method felt too good to abandon. Somewhere between those two extremes, the seeds of a new understanding of gravity were taking root. By the late 19th century, the Mercury problem had become a tiny splinter in the otherwise smooth body of Newton's universe. Every planet slowly rotates its elliptical orbit over time, a motion called precession. Most of that drift is exactly what Newton's law predicts, once you account for the tugs from other planets. But when careful astronomers did the sums for Mercury, they kept finding a stubborn leftover. After subtracting all the known effects, the point of closest approach to the Sun still advanced by roughly 43 arc-seconds per century, more than expected. That is a shift so small you could miss it if you blinked, yet big enough that it refused to be swept under the rug. If you had built your entire career on Newton's gravity being the final word, that leftover would feel like a personal insult. So people try to explain it away. Some proposed that the Sun might not be a perfect sphere, that it might be slightly squashed and therefore pull on Mercury in a more complicated way. Others suggested belts of small bodies inside Mercury's orbit that together could mimic a planet. A few clung to Vulcan itself and argued that we simply had not looked at the right moments. Each patch seemed reasonable at first glance. None of them cleanly matched the data without causing trouble elsewhere in the solar system. Underneath all the clever fixes lurked a quiet fear. What if the problem was not with Mercury, or with some missing object, but with gravity itself? Imagine waking up one morning to find that the basic rule you had used to understand the sky for 200 years might be slightly wrong. Not wrong in a way that ruins bridges and artillery tables, but wrong in the deep foundations. How many of us would really be ready to accept that? How long would we keep searching for Vulcan rather than admit that our favourite law needed an upgrade? While observatories were chasing ghosts near the Sun, a young patent clerk in Switzerland was turning the gravity problem inside out. Albert Einstein had already shaken physics with special relativity, a theory that said the speed of light is the same for everyone and that time and space twist to protect that cosmic speed limit. But special relativity mostly ignored gravity. It worked best for objects moving freely with no weight, like spaceships drifting far from stars. The real universe is full of gravity wells, and Einstein knew he had only told half the story. He began to ask a deceptively simple question. What does it actually feel like to be in a gravitational field? If you stand in an elevator on Earth, you feel your weight pressing down through the floor. If that elevator cable suddenly snapped and the cabin fell, you would feel weightless, at least until the crash. For the brief time of freefall, you and the elevator would accelerate together, and any objects you dropped would float beside you. It would feel exactly like being out in deep space, far from any planet. Einstein realized this was not just a curious thought experiment, it hinted at something profound. If freefall in a gravitational field feels indistinguishable from drifting in empty space, then maybe gravity is not a normal force at all. Maybe it is a sign that space-time itself is curved, and that objects are simply following the straightest possible paths through that curved landscape. In that picture, there is nothing pulling Mercury around the Sun in the way a string pulls a ball. The Sun reshapes the geometry around it, and Mercury moves along that shape as naturally as a rolling marble follows the bends of a track. You can imagine this with a fabric analogy. Picture stretching a rubber sheet tightly, and then placing a heavy ball in the center. The sheet sags and any smaller ball you roll nearby will move in curved paths, not because a mysterious force reaches out from the big ball, but because the surface it is moving on is no longer flat. The analogy is not perfect, but it captures the key idea. Mass and energy tell space-time how to curve. Curved space-time tells matter and light how to move. If that sounds almost poetic, it is also a brutal mathematical challenge. For nearly 10 years, Einstein wrestled with the equations needed to turn this vision into a working theory. He read up on advanced geometry, called tensor calculus, and leaned heavily on mathematician friends when the tools exceeded what he had learned as a student. He tried one set of equations, realized they gave nonsense answers, backed up, and tried again. His notebooks from that time are full of crossed-out symbols and desperate side calculations. More than once he thought he might never finish. And yet that tiny mismatch in Mercury's orbit stayed there like an itch. If the old picture of gravity could not quite handle Mercury, maybe the new, curved space-time framework would. At some point in this long struggle, Einstein took Mercury's anomaly as a kind of test. Either his theory would reproduce that 43 arc-second drift with no extra planets, or it would fail, and he would have to go back to the drawing board. Imagine the tension of setting your life work up against a single stubborn number from the sky. In November of 1915, after years of false starts, Einstein finally wrote down the set of equations he believed were right. They are now called the field equations of general relativity. They describe how matter and energy curve space-time and how that curvature guides motion. Immediately he applied them to the Sun and Mercury. The calculations were so intense that he worked late into the night for several days, chasing terms, checking approximations, making sure he had not dropped a sign or a factor. When he compared the result to the observed anomaly, he could hardly believe it. His theory predicted exactly the extra precession that astronomers had measured, and that Newton's law could not explain. No Vulcan was needed, no belts of rocks, no oddly shaped sun. The extra drift dropped out naturally once you treated space and time as a curved four-dimensional fabric, rather than a rigid stage. Einstein later said that when he saw this number fall into place, he felt a rare moment of deep calm after years of tension, as if he had finally tuned an instrument until the notes stopped wavering and rang true. For him, it was the most satisfying calculation he ever did. From that moment on, Vulcan was doomed. If Mercury's motion could be explained without a hidden planet, then all the sightings near the Sun had to be something else. Sunspots, small asteroids passing at the wrong time, eyes and instruments tricked by glare. Some defenders tried to keep the idea alive a little longer, suggesting that there might still be small bodies inside Mercury's orbit that general relativity had not ruled out. But the romantic picture of a hot inner planet with iron mountains and a proud name was gone. There is something almost painful in that. An entire world that lived for decades on chalkboards and in newspaper stories simply evaporated because a better theory made it unnecessary. If you had spent your life searching for Vulcan, or if you had believed that your own observation had finally caught it, watching it vanish into history would have felt like a personal loss. Yet this is how science keeps itself honest. The same logic that made Leverrier's prediction of Neptune so powerful is what eventually killed his second claim. A method that works has to be allowed to work against us as well as for us. General relativity did not just clean up Mercury's orbit, It also made bold new predictions that Newton's theory could not. It said that light passing near a massive object should bend slightly, as if space itself acted like a lens. It said that clocks deeper in a gravitational field tick more slowly than clocks far away. It allowed solutions where space-time could collapse into such intense curvature that not even light could escape, the objects we now call black holes. It even hinted that the universe as a whole might not be static, but expanding or contracting. For a theory this radical, one internal success with Mercury was not enough. The next question almost everyone asked was simple: can we see starlight bend? The Sun is massive enough to produce a measurable deflection in the apparent position of stars whose light passes close to its surface, but you cannot normally see stars right next to the Sun because of the glare. The only way around that is during a total solar eclipse, when the Moon slides exactly between Earth and Sun and turns day into a brief twilight. This challenge set up one of the most dramatic experiments in the history of astronomy. In 1919, less than a year after the end of the First World War, teams of British scientists, led by Arthur Eddington, travelled to two different locations along the path of a total eclipse. One team went to the island of Principe off the west coast of Africa. The other went to Sobral in Brazil. Their plan was straightforward in concept and extremely difficult in practice. Take photographs of the star field near the darkened Sun during the eclipse, then compare the apparent positions of those stars to photographs taken when the Sun was elsewhere in the sky. If the stars seemed slightly shifted outward during the eclipse, that would mean their light had been bent while passing near the Sun. Newton's theory predicted one amount of bending. Einstein's theory predicted roughly twice that amount. For you and me, the difference between these two small angles would be invisible. For the astronomers hunched over glass plates, squinting through microscopes while mosquitoes whined in the humid air, the difference would decide whether gravity was a force reaching across space, or a sign that space itself was warped. The expedition was almost a disaster. Clouds interfered, equipment malfunctioned. The photographic plates were not as sharp as anyone had hoped. Back in England, Eddington and his colleagues argued about which images were reliable enough to use. When they finally announced their results, the best set of measurements supported Einstein's prediction within the messy error bars. The starlight had bent, and by about the amount general relativity demanded. Newspapers went wild. Headlines declared that Newton's law had been overthrown, and that a German scientist no one outside physics had heard of before the war had rewritten the universe. Einstein, who had spent years working in near obscurity, suddenly found his face on front pages. He became a symbol of a new age, where space and time were flexible, and familiar concepts like absolute simultaneity and straight lines were no longer sacred. You can still feel a faint echo of that cultural shock today, when people say that everything is relative, even when they misunderstand what the theory actually says. What matters for our story is that Mercury's misbehaviour and the ghost of Vulcan both turned out to be signals that our mental picture of gravity needed an upgrade. The universe had not broken Newton's rules out of spite. It had always followed deeper rules that Newton did not know about. And those deeper rules only became visible once our measurements and our imagination were sharp enough. From a distance, it looks like a smooth story of progress. Up close, it is a tale of human stubbornness, hope, embarrassment, and eventually humility. It is also a warning that should feel uncomfortably modern. How many ideas do we still cling to today because they have given us real successes in the past? How often do we respond to anomalies by inventing new invisible entities rather than questioning the framework that made those entities seem necessary? Dark matter and dark energy are the obvious examples floated in debates now, but the pattern runs through medicine, economics, climate science, and our everyday beliefs. When something does not fit, do we reach for Vulcan? Or do we dare to ask whether space-time itself needs to curve a little in our minds? There is another angle to this story that matters for what comes next. While Einstein was refining equations on paper, other people were asking a far more explosive question. If gravity is the shape of space-time, Can we build machines that briefly escape that shape? Rockets had been toys and military curiosities for centuries, but in the early 20th century, a handful of dreamers began to see them as tools to climb out of our local gravity well entirely. If general relativity promised that objects could follow new paths through curved space-time, rockets were the crude engines that might actually push us onto those paths. In the decades that followed, the same human mix of ambition, rivalry, and short-sightedness that had made and unmade Vulcan would play out again with metal and fire. Nations would pour talent and treasure into launch vehicles, cancel them at the moment of success, and sometimes leave lonely hardware circling Earth long after the bureaucrats had forgotten it existed. Somewhere up there, even now, is a little satellite called Prospero, a relic of a country that briefly built its own road to orbit and then walked away. Prospero is still up there right now, circling our planet again and again in a silent path that almost no one looks at. No live stream, no regular contact, just a small, aging machine carrying the memory of a decision that a nation made in the early 1970s and then tried to forget. If you step back from the glamour of moon landings and space shuttles and think about that one lonely satellite, it forces an uncomfortable question. How do you build your own road to orbit, prove that it works, and then deliberately tear it up behind you? To understand how that happened, you have to imagine Britain right after the Second World War. The country had survived bombing raids and rationing, helped crack Nazi codes, and played a part in the birth of radar and jet engines. For a generation of engineers, it felt natural to assume that Britain would also stand at the front of the new age of rocketry. German V-2 missiles had already shown what long-range rockets could do in the worst way possible. The obvious next step was to take that brutal technology and try to turn it into something more controlled and more useful. Early on, the focus was military. The same physics that can lift a satellite to orbit can also deliver a warhead across continents. The British programme called Blue Streak began as an effort to build an independent nuclear-capable missile. It was a towering cylinder of metal and propellant, tested on remote ranges, with the Royal Aircraft Establishment and industry partners pouring their skill into every weld and valve. If you were an engineer working on it, you might have felt that you were helping your country secure its place among the superpowers. Then the strategic logic started to shift. Missiles buried in concrete silos looked increasingly vulnerable compared to submarine-launched weapons hiding under the ocean. Economics bit hard too. Britain had a damaged economy and a long list of competing priorities. Eventually, Blue Streak as a weapon was cancelled. On paper, the decision was rational. In reality, it left a lot of clever people with an awkward question. What do you do with a nearly finished rocket that no longer has a military job? One answer was to turn it into a laboratory. Blue Streak hardware and expertise fed into a test vehicle called Black Knight. This slim, elegant rocket flew from a remote site in Australia and carried scientific instruments high above the atmosphere to study re-entry physics. Each launch was a mix of terror and wonder. On the ground, you had teams staring at rows of dials and strip charts, listening to static-filled radio voices. In the sky, you had a streak of fire accelerating into the thin air, then a brief arc in the dark before the capsule crashed back down again. Black Knight flights gave Britain something crucial. They turned spreadsheets and wind tunnel estimates into real data. They proved that British-designed rockets could ignite, stage, and survive the brutal heating of descent. They also gave a generation of engineers the kind of hands-on experience you cannot get from reading foreign manuals. If you mentally place yourself on that windswept desert range, watching a vehicle that you designed roar away from the pad, you can feel the temptation building. If we can do this, why not go further? Why not push all the way to orbit? That is where Black Arrow comes in. Where Black Knight was a test bed, Black Arrow was a true satellite launcher. It was small compared to the heavy machines being built in the United States and the Soviet Union. It could only lift a modest payload to coax every last bit of velocity out of their propellant. Piece by piece, Britain was quietly assembling the means to put its own objects into orbit without anyone else's permission. The path was anything but smooth. Test flights failed. One vehicle never reached the planned altitude because of a guidance problem. Another broke apart. Each time, the people involved had to sift through fragments, telemetry traces, and archived design decisions, looking for the root causes. In those moments, it would have been easy for politicians to say that the whole thing was too risky and too expensive, and that larger allies already had powerful rockets that Britain could simply rent time on. In fact, that is almost exactly what happened. By the late 1960s, the British government was under intense pressure to cut costs. The country was wrestling with inflation, industrial unrest, and the long, slow process of redefining itself after empire. At the same time, it was pouring money into other high-profile technology projects, like the supersonic passenger jet Concorde, which was supposed to prove that Britain and France could still lead the world in glamorous engineering. Compared to a sleek, white airliner that ordinary citizens could imagine riding one day, a stubby black rocket flying from a remote desert was a hard sell. Space also had a diplomatic dimension. Being seen as a good partner inside wider European collaborations mattered. So did the relationship with the United States, which was offering access to its heavy launchers. Why spend scarce funds duplicating what a friendly superpower already had? Committees produced reports. Reports produced options. Options turned into neatly worded recommendations to wind down domestic launcher development and focus on building satellites instead. The logic on paper was tidy. You could still do space science and communications. You would just hitch rides on someone else's vehicles. If you step into the shoes of one of those engineers, though, that tidy logic feels different. Imagine spending your 20s and 30s working through sleepless nights to make valves behave, solving control problems, watching test stands shake, and learning with each small fire and each near miss. Then imagine being told that your country will never again need its own rocket because it is cheaper to buy space on a foreign one. You would probably nod in the meeting and then go home at midnight and stare at the wall, wondering whether all those launches were just rehearsals for a performance that would never happen. In an odd twist of timing, the Black Arrow program was cancelled in 1971, just before it did the one thing it had been designed to do. The cancellation meant that the very next launch would also be the last. Hardware was already built, teams were already deployed. Scrapping that final mission would have wasted years of work and millions of pounds for no practical saving. So the government allowed a kind of technical farewell. One last shot, one final climb into orbit. The launch site was Woomera in South Australia, a vast test range shared under international agreements. If you had been there on that October day, you would have seen a surprisingly small rocket standing on its pad against a clear, harsh sky. Black Arrow did not have the skyscraper scale of a Saturn V. It looked almost modest, with its black and white paint and its clustered engines. Yet inside its nose sat a small satellite called Prospero, named after a magician in an old play who gives up his powers in the end. The symbolism is hard to miss now, but at the time it was mostly a practical choice. Prospero carried instruments to test new technology for communication satellites, especially novel materials for antennas. If everything worked, it would send back data that might make future British-built payloads more capable, even if they were launched on foreign rockets. Countdowns are long, they are also fragile. A single bulky valve or suspicious sensor can stop the whole process. That day the count held a few times while teams checked readings. Then the range went green. The engines lit, a tongue of flame dug into the concrete flame trench, and Black Arrow began to rise. Slowly at first, then faster as the fuel burned and the weight dropped. From a distance it might have looked like a bright needle drawing a line into the blue. Up close it was a deafening, shaking event, the kind of thing that pounds into your chest and lodges in your memory forever. Stage separation worked. The upper stage took over. Prospero rode a narrowing plume of fire until the engines shut off and everything went quiet. For a moment, the satellite and the spent rocket stages coasted together in the cold, thin edge of space. Then springs pushed Prospero gently away, and small systems woke up, unfolding, stabilizing, beginning to talk to the ground. In tracking stations thousands of kilometers away, lines of numbers began to march across screens, confirming that Britain had done it. With its own machine and its own launcher, it had joined the club of nations that had put a payload into orbit on their own. You might expect that moment to trigger celebrations and renewed funding. In another timeline, perhaps it would have. In ours, the decision had already been made. Black Arrow was dead, and Prospero was its last act. The launchers under construction would never fly. The test stands would fall silent. Young engineers who might have spent their careers refining and extending that capability drifted into other fields or took their skills abroad. Prospero itself did its modest job well. For years it sent back measurements about how different materials behaved in the harsh environment above the atmosphere. Once the mission goals were met, controllers shut down transmissions, and the satellite became just another faint blip in catalogues of orbital debris. Yet it was different from most of the other objects up there. It was not just a leftover, a spent stage, or a dead experimental platform. It was the only satellite Britain ever launched on a rocket entirely its own. Every time it passes overhead, it carries a quiet counterfactual with it. What would British spaceflight look like today if that final success had been seen as a beginning instead of an end? Would there be a whole family of refined Black Arrow descendants by now? Would small British launchers have played a role in the satellite boom of the late 20th century? Or was the country always destined to trade that independence for access to bigger foreign rockets and a seat at multinational launch platforms? This is not just a story about one country. It is a pattern that repeats worldwide. Ambitious programs are started by politicians who want headlines, nurtured by dedicated teams, and then cancelled by new leaders faced with different budgets and different priorities. When you see an old rocket carcass in a museum or a silent satellite in a catalogue, you are looking at the physical fossil of a decision that someone made in a meeting room decades ago. The fossil does not argue back. It just orbits or sits behind glass, while we carry on telling ourselves that the path we took was inevitable. There is also a psychological echo of Vulcan here. In the 19th century, some astronomers clung to an invisible planet because it fit too well with their story about how the universe ought to work. In the 20th century, some governments abandoned working rockets because they did not fit with their story about what the nation ought to spend money on. In both cases, reality had the final word. The sky did not care whether you believed in Vulcan. Orbit did not care whether the rocket had a British flag on its side. The only difference was who got to leave their signature in that sky. If you feel a little frustrated on behalf of Prospero, that is a healthy reaction. Frustration means you are noticing the gap between what was possible and what was chosen. Those gaps are where history usually hides its most revealing lessons. Think about your own country for a moment. Where have similar choices been made? Where have remarkable capabilities been built up just long enough to prove they work, and then dismantled again before they could reshape the future? The thread running through all of this is simple. Our technologies are not just tools, they are expressions of what we value and what we fear. We build rockets when we feel a need to reach beyond our current limits, or when we are afraid of others doing it first. We cancel rockets when the price seems too high, or when other projects promise more prestige for fewer headaches. Somewhere between those pushes and pulls, a small satellite ends up circling the Earth for half a century as a reminder. Prospero never came down. It just kept looping through its orbit while human attention moved on. New generations grew up with images of American shuttles, Russian Soyuz capsules, and international space stations. If they heard the name Prospero at all, it was as a trivia note. Meanwhile, the larger space race accelerated. Superpowers began to ask not just whether they could reach orbit, but whether they could put living beings there and keep them alive long enough to do serious work. That shift from simple up and down flights to real habitation is where the story turns next. It is one thing to light a rocket, throw a machine into orbit and walk away. It is another thing entirely to strap a human being to that fire and promise their family that you will bring them back. The first attempts to do that looked more like controlled emergencies than routine transport, and they raised a new question that would dwarf debates about Vulcan or Prospero. Could fragile bodies and minds really survive even a few hours in the hostile environment above the air? The hostile environment above the air was not just a poetic phrase, it was a genuine unknown. For most of human history, the sky had been a ceiling you could look at but never touch. Balloons and high-altitude aircraft had pushed that ceiling upward, but only a little. Pilots came back from extreme flights with bloodshot eyes, bruises from pressure suits, and strange stories about the way their minds felt when oxygen ran low. Doctors argued about whether a human body would even work if you took it out of the comforting pressure and gravity it had evolved in. At the same time, governments were quietly learning from weapons. In the final years of the Second World War, German V-2 rockets had arced high above Europe before slamming into cities. The Allies' captured hardware and engineers was the ugliest use. Throwing warheads was the ugliest use. Throwing warheads across continents. The other was almost unthinkably ambitious, throwing instruments and, perhaps people, all the way into orbit. The Soviet side moved first. Under the direction of a brilliant, once-imprisoned engineer named Sergei Korolev, they clustered their experience into a family of launchers called R-7. Officially it was a missile, but everyone at the top understood that it could be used to loft something far more symbolic than a weapon. In 1957, that something became a polished metal sphere with 4 spidery antennas. When the rocket lit and the sphere reached orbit, it began to send a simple, repeating radio signal back to Earth, a steady pattern any amateur with the right receiver could hear. For ordinary people, the first artificial satellite, Sputnik, was eerie and beautiful. For military planners in Washington, it was terrifying. If the Soviet Union could put a small object into orbit, it could also toss warheads on any city on Earth. The sight of a point of light drifting across the night sky, paired with that beeping signal on shortwave radios, drove home the message in a way no report could. The psychological impact was enormous. Newspapers ran anxious headlines. Parents worried about their children growing up under a metal eye. The United States hurried to answer. An early attempt to launch a satellite with a rocket called Vanguard failed on live television, the vehicle rising only slightly before sagging back and exploding in a fireball. The footage played again and again. Commentators joked bitterly. The contrast with the crisp success of Sputnik was brutal. Behind the jokes, though, there was a growing determination. If the Soviet Union had thrown the first stone into the sky, the United States did not intend to stay on the ground. In 1958, the United States government reorganized its scattered aeronautics and space projects into a single civilian agency, the National Aeronautics and Space Administration. It inherited wind tunnels, test pilots, and a culture of cautious engineering from the old National Advisory Committee for Aeronautics. It also inherited the pressure of a strategic race it had just lost the first round of. In quiet conference rooms, people began sketching not just better rockets, but the outlines of an entirely new kind of mission. What if the next object in orbit carried a living human being? This was the birth of Project Mercury. The goals written on paper were deceptively simple. Put a person in space, bring them back safely, learn enough about their body and mind in that environment to make more ambitious missions possible later. The reality behind those lines was a maze of problems. You had to figure out how to place a small capsule on top of a missile built for war, keep it intact through launch, keep its occupant alive in weightlessness, and then protect them when the whole thing slammed back into the thick air at tremendous speed. Doctors did not agree on what would happen during that middle phase. Some worried that the lack of weight would make it impossible to swallow or to move eyes properly. Others wondered whether blood would pool strangely, or whether inner ear signals would scramble the sense of up and down so badly that astronauts would become useless. There were genuine fears that the first person in orbit might simply lose consciousness and never regain it. In that climate of uncertainty, every decision about capsule design and crew selection carried heavy weight. NASA chose its first astronauts from a pool of test pilots used to wrestling unstable aircraft through dangerous envelopes. These men had flown experimental jets at the edge of their performance, sometimes losing friends in the process. They were used to trusting instruments when their senses lied, and to making rapid decisions under crushing acceleration. To them, being strapped into a tiny capsule on top of a missile was another extreme assignment, but they also bristled at the idea of being mere passengers. They wanted some control, some way to fly the machine, not simply ride it. The Mercury capsule that took shape around them was shockingly small. On the outside, it looked like a blunt cone with a thick heat shield on the base. On the inside, it was a padded, contoured seat surrounded by switches, small windows, gauges, and cramped life support plumbing. Every kilogram had to justify itself. There was room for one person, strapped in so tightly that even turning the head was an effort. Engineers argued over whether the capsule should be fully automated, or whether the pilot should have manual thrusters and control sticks. Under that argument lay a deeper question. Was the first American in space going to be a human payload or a pilot? In the end, the compromise was delicate. The systems were designed to operate automatically, with ground control commanding much of the sequence. But there were backup controls that a trained astronaut could use if things went wrong. This was not just about pride. It was a hedge against unknowns. If a sensor failed or a computer glitched, a human brain might still thread a path home. Before anyone let a human climb into that can, they tested it with dummies and animals. Small rockets called Little Joe blasted test capsules into high arcs to simulate the brutal forces of launch and aborts. Parachutes were deployed. Escape towers were fired to yank capsules away from failing boosters. In other flights, monkeys and chimpanzees were wired up with sensors and trained to perform simple tasks, so that doctors could see whether weightlessness affected their performance. High-altitude research aircraft and centrifuges on the ground tried to mimic the experience, but everyone knew that nothing matched the real thing. While this was happening, the Soviet program was sprinting down a parallel track. Their spacecraft design, called Vostok, was larger than Mercury and used a spherical re-entry cabin. Korolev and his team approached the problem with a somewhat different philosophy. Their system leaned more heavily on automation, with less direct control from the cosmonaut inside. They chose their first crew from a group of military pilots as well, but they kept much about the selection and the training process wrapped in secrecy. To the outside world, it looked like a shadowy race, the details hidden behind slogans and carefully staged photographs. In April of 1961, the Soviet side crossed a line that no one had ever crossed. Yuri Gagarin, a young pilot with a quick smile and a calm demeanor, sat down in the cockpit of Vostok 1 atop a rocket on the Baikonur steppe. He heard the fueling lines disconnect and the engines roar underneath him. He felt the weight increase as the rocket accelerated upward, pressing him into his seat. As the atmosphere thinned and the engines finally shut down, he experienced the strange sensation of his body floating against the restraints. For the first time, a human being was circling the Earth, looking down on continents and oceans from the outside. Gagarin completed a single orbit. His ship automatically oriented itself for re-entry. On the way down, at a high altitude, he ejected and descended the rest of the way by parachute, landing in a field where farmers and their families stared in astonishment. News of his flight raced around the world. In the United States, it landed like an electric shock. The Soviet Union had not only put the first satellite into orbit, it had now put the first person there as well. The gap that American planners thought they could quietly close had just widened. Inside NASA, this produced a mix of embarrassment and fierce motivation. Project Mercury was already underway, but its pacing suddenly felt slow. Timelines were revisited, missions were reshuffled. The agency needed a visible success, and it needed it soon. One of the most ready vehicles was the Mercury capsule atop a modified Redstone missile, which did not have the power to reach orbit, but could perform a suborbital flight, arcing up into space and then back down into the Atlantic. This would not match Gagarin's achievement, but it would at least prove that an American could ride a rocket and survive. The first American scheduled to make that ride was Alan Shepard. He had trained exhaustively in simulators and centrifuges, endured endless hours in pressure suits, and memorized procedures. On launch day, he lay on his back in the tiny cabin of his capsule, hearing the count tick down. The redstone beneath him was a direct descendant of earlier military missiles, refined and adapted. When it ignited, the acceleration was brutal and loud. Shepard felt gravity multiply, his body pushing into the couch, his vision almost shimmering. Then came the sudden lightness as the engine cut off and the capsule coasted upward into the black. For a few minutes he experienced weightlessness. Small objects floated in front of him. The horizon out the window was curved and strange, with a thin band of atmosphere glowing against the darkness. He reported back to the ground that he was fine, that he could work the controls, that the experience of floating did not rob him of his ability to think. Then gravity returned as the capsule fell back, the heat shield flared orange and white, and the parachutes opened. When recovery crews pulled him from the ocean, he was smiling, but everyone involved knew how fine the line between success and disaster had been. A second suborbital Mercury flight with Gus Grissom followed. This time, almost everything in the flight itself worked. The capsule flew its arc, re-entered, and deployed its chutes. After splashdown, though, the hatch blew unexpectedly. Water rushed in. Grissom barely escaped before the capsule sank. The incident sparked fierce arguments about whether he had triggered the hatch prematurely, or whether a malfunction was to blame. It also underlined how many ways a mission could still go wrong, even after the main test had been passed. Getting up and getting down alive were related but separate arts. The real psychological turning point for the American public came with the first orbital Mercury mission. That belonged to John Glenn. His flight rode not on a Redstone, but on an Atlas, a slender rocket originally designed as an intercontinental missile. The Atlas was powerful enough to place the capsule into orbit, but it had a reputation for structural fragility. Engineers joked nervously that it was a balloon tank that had to be kept pressurized to stay rigid. Launching a person on it required faith in thousands of parts working together. During Glenn's flight, a warning light suggested that his heat shield might not be properly attached. Ground controllers worried that it could come loose during re-entry, exposing the thin metal underbody of the capsule to lethal heating. At that time, there was no way to inspect the shield in orbit. The only choices were to cut the mission short or to accept the risk and hope that an improvised plan would help. They chose the latter, commanding the retro rocket pack to remain strapped to the bottom of the capsule during descent, in the hope that its straps would hold the shield in place. As Glenn came down through the atmosphere, pieces of burning material streaked past the small window. For a few tense minutes, everyone on the ground feared they were watching the capsule break apart. Only when the parachutes opened and clear radio calls came through did the tension break. Later analysis suggested that the heat shield had been fine and that the warning light was false, but in the moment the incident underscored how thin the margin for error remained. A single indicator, a single strap, could mark the line between a national triumph and a tragedy. By the end of Project Mercury, the United States had flown several manned missions. Astronauts had coasted weightless for hours, eaten small meals, and performed limited experiments. They had tested whether hands could still move precisely, whether eyes could focus, whether medical sensors showed any alarming changes. The answers were cautiously reassuring. Human beings could survive short periods in space and function well enough to operate controls and make decisions. The Mercury capsules proved that you could launch a person on top of a converted missile and have them come home alive, more than once. But the limitations were obvious too. Mercury was not designed for comfort or long stays. The cabins were cramped to the point of claustrophobia. The flights lasted hours, not days. There was no room to move around, no way to change clothes, very limited ways to sleep. Basic hygiene was a problem. The missions were more like high-stakes sprints than true living in orbit. If the goal was to eventually send people to the moon and back, or to build stations where crews could stay for weeks, a new kind of training and a new kind of spacecraft would be needed. Beneath the headlines about brave men and roaring rockets, one detail from Mercury pointed quietly toward the heart of that transformation. Before Alan Shepard ever felt weightlessness, before television audiences watched John Glenn orbit, another passenger had already ridden a Mercury capsule on top of a redstone. He did not understand the stakes. He had no vote in the matter. He was a young chimpanzee, trained to pull levers when lights flashed, his tiny hands a stand-in for ours. His flight would go almost catastrophically wrong, and still change the minds of cautious doctors watching from the ground. The young chimpanzee who climbed into the Mercury capsule that winter morning knew none of this. He did not know about Gagarin or Glenn, did not care about prestige or missile gaps. He knew that when a light came on, he could pull a lever and receive a food pellet. He had learned that if he did not, he might feel a small electric buzz on his feet. In his world it was simple. Stimulus, response, reward, discomfort. In our world, miles away in control rooms and offices, people were using that simple learning to decide whether it was safe to send one of us. His name was Ham, chosen later from an acronym tied to his training base. Before that, he was just one of several chimpanzees captured in Africa, shipped across oceans, and brought to a facility in New Mexico, where the United States Air Force and NASA were running a series of experiments. The chimps were chosen because their bodies and brains were close enough to ours to act as proxies. They could wear suits, sit in chairs, work controls, and show whether tasks became harder when the environment became more extreme. If the chimps coped well, doctors reasoned, humans probably could too. The training was intense. Technicians built small mock-ups of the Mercury cabin and strapped the chimps into them for hours at a time. Lights would flash in front of their faces. If a particular colour appeared, a lever had to be pulled within a short window, pull quickly and correctly, and a reward pellet dropped into a small tray. Fail or hesitate, and a mild electric shock pulsed through the footrest. At first the chimps were confused, pressing levers at random, flinching at the shocks. Over weeks they became faster and more accurate, until the sequence of light and motion became almost automatic. From the outside this looks cold, even cruel. From the inside it was a calculated way to answer a specific question. Would the stress of launch, the heavy acceleration, the disorienting weightlessness, and the loneliness inside a sealed cabin disrupt the ability to perform learned tasks? It is one thing to measure heart rate and blood pressure during a simulated flight. It is another to see whether a mind can still focus and respond. The lever and the light made that visible in a way a passive passenger never could. Ham stood out during training. He was quick, curious, and less easily rattled than some of the others. He recovered faster when new noises or sensations were introduced. The trainers came to see him as reliable, even under pressure. That reputation, built from repeated tests and charts and internal reports, is what eventually placed him at the top of the list when the time came to choose a candidate for a real flight. If you imagine Ham sitting in his enclosure, grooming himself or playing, you can feel the strangeness of that moment. One animal, with no say, about to be strapped to an experiment that humans considered too risky for one of their own. On the morning of the mission, Ham was suited up and placed inside a specially shaped container that locked into the Mercury capsule. Sensors monitored his heartbeat, breathing, and brain activity. The lever and light panel were positioned in front of him, just as in training. Outside, the redstone rocket that would carry him to the edge of space stood venting small clouds of chilled propellant into the cool air. Technicians and engineers moved back and forth under its tall frame, checking valves and cables, listening to radios. For them, this was another test flight in a long series. For the doctors watching, it was something sharper. The first time a living primate would ride a Mercury system through its entire profile. As the countdown rolled towards zero, Ham sat in darkness, surrounded by the quiet hum of pumps and electronics. He had been through simulated countdowns before, but those ended in vibration tables or centrifuges on the ground. This time, when the final sequence began, the base of the rocket came alive with tearing sound and fire. Acceleration slammed through the structure. The force drove Ham back into his couch. His breathing quickened. The sensors on his body registered the shock, sent it tumbling back to consoles far away. From Ham's point of view, the world had suddenly turned into a loud, crushing tunnel. Yet when the first light flashed on his panel, he still pulled the lever within the correct window. Even as the G-forces climbed, his trained response stayed intact. That single act mattered enormously to the humans watching. It suggested that a trained brain could keep working, even under stresses no one had ever experienced before. At least, that was true for the first part of the flight. Then the rocket began to misbehave. Because of a fault in the automatic controls, the redstone burned longer than planned. Instead of following the intended shallow arc, the vehicle pushed Ham higher and faster. The acceleration exceeded what doctors had planned. The trajectory carried the capsule much farther downrange than expected. In technical language, the flight went long. In human terms, everything was now happening outside the safe lines the planners had drawn on their charts. If you imagine sitting in the blockhouse, listening to numbers being called out that no longer match the plan, you can feel the tension rising. Inside the capsule, the environment went from intense acceleration to the eerie calm of weightlessness. Straps that had been pressed hard against Ham's body now floated slightly. Loose objects drifted. His body, tuned by a lifetime of gravity, tried to reconcile signals from the inner ear that no longer matched any experience he had ever had. Despite that, when the light flashed, he still pulled the lever. His reaction times were longer and his accuracy dropped somewhat, but he continued to perform the task again and again throughout the period of weightlessness. The data told a complicated story. For the doctors, this was gold. It meant that he was still alive and well. For the doctors, this was gold. It meant that humans, who might find weightlessness emotionally strange but conceptually understandable, would almost certainly be able to function even better. But that conclusion came later. In the moment, they had a more immediate problem. Because of the trajectory error, the capsule was now headed for a different splashdown point than the recovery ships had been told to expect. Re-entry began with a roar and the crackling rise of heat. The small Mercury capsule slammed into thicker air, its blunt heat shield turning kinetic energy into searing plasma. Inside, Ham experienced another long wave of crushing force, the G-meter climbing beyond what his trainers had hoped he would ever feel. Yet his body survived it. The shock abated, the main parachute deployed. The capsule dropped toward the Atlantic, bobbing violently as it hit the waves. For a moment, everyone in the control centers must have felt a release of tension. The arc was complete. All that remained was to pick up the vehicle and bring the occupant home. Then new telemetry began to arrive that turned relief into renewed alarm. The capsule's hull had been punctured on impact, and water was leaking into the cabin. As it rode the swell, it threatened to roll and submerge. Ham, strapped into his container, could not escape on his own. If the capsule sank before rescue crews arrived, he would drown, still wired to the experiments that had been his taskmaster for months. Somewhere in the mission control rooms, people who had made calm, theoretical arguments about acceptable risk now saw those arguments change into a frightened animal battling seawater. Helicopter crews and naval ships were already racing toward the projected impact area, but now they had to adjust for the unexpected downrange distance. The ocean is vast. A small capsule rising and falling on waves is easy to lose. Pilots scanned the surface, eyes straining against the glitter. Finally, a splash of orange and white came into view. The helicopter approached, hovering in the blasting wind from its own rotor wash. Swimmers dropped into the water, fighting the turbulence, and worked to attach lines to the capsule. From inside, Ham would have heard thunderous noise and felt new jolts as the craft was hauled partly clear of the waves. At one point, the capsule tilted dangerously, threatening to dump more water into the cabin. On the helicopter, crew members wrestled with the swaying load. Eventually, they managed to haul the capsule up, secure it, and fly back toward the recovery ship. When the hatch was finally opened and Ham emerged, wet but alive, he seemed surprisingly calm. There is a famous photograph of him sitting in the arms of a crewman, lips drawn back in what looks almost like a grin, his eyes bright and alert. People interpret that expression in different ways. Some see simple animal relief. Some see a bizarre echo of human astronauts smiling for cameras after their missions. Whatever he was feeling, his survival meant that the data from the mission could be treated as proof that the Mercury design, even when everything did not go according to plan, could carry a living being through the full sequence. It also meant that the doctors and managers who had signed off on sending a chimpanzee instead of a person could tell themselves that they had chosen correctly. The risk had been real. The subject had lived. The program could move on. This is the point where you and I have to sit with an uncomfortable question. Was that bargain acceptable? Is it right to strap an animal into a capsule with no understanding of what is happening and expose it to forces and dangers that you consider too great for a human volunteer at that stage? The people involved would argue that their duty was to the future human crews, whose lives they also had a responsibility to protect. If sacrificing a chimp could reduce the odds of killing an astronaut, they believed, then the sacrifice could be justified. History is full of similar decisions. We send test vehicles down new roads before allowing buses full of passengers to follow. We run destructive tests on airbags and helmets, using dummies that stand in for fragile bodies. The difference here is that the stand-in had a mind, could feel fear and confusion, and had no way to consent. If that makes you uneasy, that unease is a clue. It shows that even in a story often told as a triumph of engineering and courage, the moral landscape is complicated. At the same time, Ham's mission undeniably changed human beliefs about what was possible. The timing of his lever pulls under launch load, the way his performance shifted during weightlessness, the pattern of his vital signs as the capsule leaked and floated, all of that went into reports that convinced cautious decision-makers that it was time to let a human climb into the same seat. Within months, Alan Shepard flew his suborbital mission. The Ark that had nearly drowned a chimpanzee now carried a naval test pilot, and through him, an entire nation's hopes into space. If you imagine being Shepard, you might see Ham's face in your mind as you strap in. You know that the system worked well enough to bring him back alive, even when parameters went out of bounds. You also know that one different failure, one unseen crack or faulty valve, could have tipped the outcome. That awareness is what makes the word pioneer feel heavy when applied to these early flights. Pioneering is not just about being first. It is about walking into conditions that no one fully understands, knowing that every line of telemetry could be writing a manual for those who come after. Ham lived for many years after his flight. He spent time at a research centre and eventually moved to a zoo, where visitors could look at him without knowing the role he had played in space history. When he died, his remains were treated with a kind of respect, parts of his skeleton preserved for study, the rest buried at a museum that honours early space efforts. That might sound like a thin reward for what he endured, yet it is more than most experimental animals ever receive. In a quiet way, he became a symbol of the hidden costs behind our most celebrated achievements. The lesson embedded in his story reaches further than rockets. It asks us to think hard about what and whom we are willing to put at risk when we chase progress. When we test new technologies, new medicines, new systems, we draw lines around who is protected and who is exposed. Sometimes those lines follow species. Sometimes they follow class or geography or age. The choices are rarely as stark as a chimpanzee versus a test pilot, but the logic rhymes. If we do not examine that logic, we risk repeating patterns blindly. Back in the hangars and design offices, engineers read the Ham mission reports and saw something more operational. They saw confirmation that a small, pressurized cabin could keep a living occupant alive through incredible stresses, even when the rocket overperformed and the landing was rougher than planned. They saw evidence that complex tasks could be performed in microgravity, and that training could build habits strong enough to survive noise, weight, and fear. Those insights fed directly into the next generation of spacecraft, which would not simply leap up and down, but would stay in orbit long enough to attempt true work. The transition from brief ballistic hops to extended stays demanded a change in mindset. Up to this point, missions had been almost like stunts: launch, coast, return. Spectacular, dangerous, but over in minutes or hours. To go further, to rendezvous with other vehicles, to dock, to carry out experiments, to prepare for journeys to the moon, space agencies would need to think of time in orbit as something that could stretch. Days instead of hours, then a week, then 2 weeks. With each increase, the questions about human endurance, behaviour and risk would sharpen again. Ham's few frantic minutes of weightlessness and his unexpected ordeal in a leaking capsule were a tiny first data point on that curve. The next steps would involve pairs of astronauts in slightly roomier cabins, trying to eat, sleep and work while circling the Earth again and again. They would grapple with vertigo, with cramped muscles, with boredom and wonder in equal measure. They would test manoeuvres that, if perfected, would make lunar missions possible and, if botched, could send crews tumbling helplessly through space. In other words, the experiments were about to shift from animals to us, and the stakes would rise accordingly. The vehicle that carried those next steps had a simple name that hid how ambitious it really was. After the single-seat capsules of the first program, the next design was called Gemini, after the twins in the night sky. The name fit. These missions would always carry 2 astronauts, working together in a space barely bigger than the front seat of a small car. They would not just visit orbit, they would try to live there long enough and skillfully enough to make a journey to the moon more than a patriotic daydream. From the outside, a Gemini capsule looked like a stretched and sharpened version of its predecessor. It had more windows and a more pointed nose, designed to carry docking equipment. Underneath it rode not on the slender Redstone or the balloon-like Atlas, but on a tougher Titan rocket, adapted from a military missile. The whole stack was taller, heavier, and far more capable. Most important, the Gemini spacecraft carried its own small maneuvering thrusters and fuel. It could change its orbit after reaching space, instead of being stuck on whatever path the booster had given it. That ability to maneuver was the heart of the program. To go to the moon, you would need to send one spacecraft into orbit around Earth, then another, then have them meet, dock, and act as a single machine. Later, you would need to repeat that dance around the moon itself. On paper, the math of orbital rendezvous was well understood. In practice, no one had ever tried to line up 2 fast-moving vehicles in the thin, high vacuum and make them touch gently without crashing or drifting apart. It is tempting to imagine that you can just point the nose at the target and burn the engines until you catch up, like a car speeding down a highway ramp to merge with traffic. Orbit does not work like that. If you speed up in the direction you are moving, you actually raise the opposite side of your orbit and can end up farther from the target. To catch up, you often have to lower your orbit, which makes you go around the Earth slightly faster, like a runner on an inner track. Then you raise it again at just the right time. It is an unintuitive game of falling and timing. Alongside rendezvous and docking, the Gemini missions had 2 other big goals. They needed to prove that people could stay in space for more than a couple of days without falling apart, and they had to learn how to work outside a spacecraft in a pressure suit, hanging over the planet with nothing but a tether between you and the void. Each of those goals came with its own stack of unknowns and fears. Doctors worried about bone loss, muscle wasting, and psychological strain. Engineers worried about suit stiffness, fogged visors, and the risk of astronauts overheating or losing control during spacewalks. The first steps toward those goals were cautious. Gemini missions began with shorter flights that focused on testing the new systems. Gemini 3, flown by Gus Grissom and John Young, checked how the capsule handled with 2 people on board, and whether small thrusters could really change its attitude and orbit the way simulators said they would. The crew even smuggled a small sandwich aboard, a light-hearted gesture that annoyed managers but hinted at the human need for small comforts in a metal box far from home. The mission that etched the idea of a spacewalk into American minds came next. On Gemini 4, Ed White became the first American to leave a spacecraft and float in open space. When he opened the hatch and pulled himself out, tethered and holding a small handheld thruster that looked like a futuristic pistol, he saw a sight that had previously existed only in imagination. Below him, the Earth rolled past, blue and white and brown, filling his field of view. There was no engine noise, only the hiss of suit systems and the quiet of his own breath. White was supposed to spend only a few minutes outside, testing how easy it was to move and whether the suit and tether systems behaved as planned. Once free, he found it hard to convince himself to come back in. He rotated slowly, fired the small thruster, and described the view to the ground in a voice that sounded both professional and awestruck. When the time came to return, he hesitated until his commander insisted. Closing the hatch was harder than expected, the suit pressurization making movements clumsy. The flight controllers watching saw beauty and risk intertwined in every frame. Those minutes revealed something important. From the ground, you might assume that floating outside a spacecraft would feel effortless. In reality, the suits were stiff, the tools awkward, and the coordination needed to move along handholds and tethers taxing. Later spacewalks on other missions would leave astronauts drenched in sweat, muscles burning, sometimes close to exhaustion. The vacuum does not forgive mistakes. If you let go or drift into a bad position, there is no friction to help you stop, only careful pulls on the tether or the patient push of a thruster. As the missions ticked by, the program began to stretch the clock. Gemini 5 remained in space for more than a week, long enough to roughly match the time a round trip to the moon would take. Gordon Cooper and Pete Conrad shared a cabin that gradually filled with the smells of stale food, suit fabric, and human bodies with no shower. They slept in shifts, strapped to their seats so they would not drift into switches. Eating meant squeezing food from small containers. Going to the toilet was an exercise in patience and ingenuity. When you imagine heroic spaceflight, you rarely picture trash bags and damp wipes, yet those were as critical to success as engine burns. The long mission revealed physical changes that would later become familiar. Muscles that did not have to fight gravity began to lose tone. Fluids shifted in the body, giving astronauts puffy faces. They reported back pain from spines decompressing. Some felt lightheaded when they returned to Earth and had to stand up against gravity again. None of these effects were catastrophic during a week, but they hinted at problems that could grow if stays became longer. Doctors took notes and began to think about exercise devices and drugs that might help. The most elegant demonstration of rendezvous skill came with a pair of flights, Gemini 6 and Gemini 7. Gemini 7 launched first, carrying Frank Borman and Jim Lovell on a long endurance mission. Their job was to prove that 2 weeks in orbit was survivable and to act as a passive target. They settled into a routine of experiments, observations, and the daily grind of living in a small can. Days into their flight, Gemini 6 lifted off with Wally Schirra and Tom Stafford on board, their capsule targeted to chase down the waiting pair. Watching the replay today, it is easy to underestimate how nerve-wracking this was. Gemini 6 had suffered a launch abort on the pad earlier, when its engines ignited briefly and then shut down. The slightest error in handling could have led Schirra to pull the abort handle and blast the capsule away, with unpredictable results. Instead, he kept his head and stayed put, trusting his instincts and the readings around him. On the successful attempt, the Titan lifted them cleanly into orbit and the real work began. Using radar and visual cues, Schirra and Stafford nudged their orbit closer to that of Gemini 7. They fired thrusters in short bursts, watching how the target moved against the stars. Little by little, the distance closed from hundreds of kilometers to mere meters. At one point, the two spacecraft flew in formation, only a few meters apart, nose to nose, while 4 human beings stared at each other across the void through thick windows. They did not dock, because the hardware for rigid connection was not on those vehicles, but they proved that the dance of approach and station keeping was possible. To understand how strange that must have felt, imagine driving on a circular racetrack in the dark with no friction and trying to bring your car neatly alongside another without bumping it or sliding away. Every tap on the accelerator changes your path in a way that takes time to show up. There is no road noise to guide you, only the glint of the other car in your headlights. Now do it at thousands of kilometers per hour, with your life and your friend's life depending on not being sloppy. That is the level of precision Gemini began to make routine. Not every attempt went smoothly. Gemini 9 had its own share of drama when the target vehicle it was meant to dock with failed to shed part of its protective shroud. Instead of a neat docking collar, the astronauts saw a twisted, partially open metal structure that looked like a mechanical flower. Docking with that would have been suicidal. They backed away. Later, during a spacewalk, Gene Cernan struggled with an overly ambitious plan to move to the back of the spacecraft and test a jet-powered backpack. His visor fogged, his suit overheating as he fought the constraints. Eventually, controllers scrubbed that part of the plan. The lesson was clear. Tools and procedures had to match the human body's limits, not just the dreams on the checklist. All of these missions built knowledge slowly, often with frayed tempers and tired eyes. Yet the moment that best captured how close the line between mastery and disaster remained came on Gemini 8. This mission was commanded by Neil Armstrong, with David Scott as his crewmate. Their plan was bold even by the standards of the program. They were to launch, rendezvous with an unmanned Agena target vehicle, and perform the first true docking, locking the two machines together into a single long stack and testing how they handled. The first part went almost eerily well. The Titan did its job. Gemini 8 reached orbit and closed in on the Agena with precision. Armstrong and Scott lined up their approach and gently eased the nose of their capsule into the docking collar. Latches engaged, indicator lights confirmed a hard mate. For a brief period, everything felt textbook. Two separate objects had become a combined spacecraft, flying together. On the ground, controllers must have allowed themselves a rare moment of satisfaction. Then the combined vehicle began to twitch. At first the movements were small, almost like a shiver. Then they grew into a steady roll. Instruments showed a spin developing, slow but building. The crew checked the Agena's systems. Suspecting a problem with its thrusters, they commanded its engines off. The spin continued and began to accelerate. Whatever was pushing on the stack was not on the target vehicle alone. Somewhere, a Gemini thruster was likely stuck open, feeding a constant gentle push that, in the frictionless environment of orbit, had nothing to counter it. Armstrong made the hard decision to undock. If the problem was in the Agena, separating might calm things down. He triggered the sequence and the clamps released. For a moment, the two vehicles drifted apart. Each should have stabilized on its own. Instead, now freed of the extra mass, the Gemini capsule began to spin faster. A stuck attitude control thruster was definitely on their own ship, and without the dead weight of the Agena, its effect was worse. The spin rate climbed beyond 1 revolution per second. At that speed, the view out the window turns into a blurred carousel. Up and down lose meaning. Blood is thrown toward the extremities, then toward the head, then back, over and over. If you have ever spun too fast on a playground ride and felt the world wobble, multiply that by a factor that makes thinking, and even staying conscious, difficult. Armstrong and Scott were being tumbled in 3 dimensions, strapped down, with panels and switches whipping past their eyes in a nauseating blur. This is where training and personality combined in a way that probably saved their lives. Armstrong had a reputation for calm under pressure long before this flight. He had flown test aircraft through chaotic situations and stayed analytical. In the spinning Gemini cabin, he methodically switched off the small thrusters that were designed for normal maneuvering, and instead activated a separate set of jets that were normally reserved for re-entry control. Using those more powerful but limited fuel thrusters, he fought against the spin, pulsing them in bursts that gradually slowed the rotation. The fuel gauge on that system ticked downward. There was no way to refill it. If he used it all up, they would be left with no stable way to orient the capsule for the fiery plunge back into the atmosphere. On the ground, controllers watched numbers that suggested a grim trade-off. Use too little, and the spin might continue until the crew blacked out, began to fall. The cost of that victory began to fall. The cost of that victory was the mission itself. With the re-entry control fuel largely spent, there was no choice but to end the flight early. Gemini 8 fired its retro rockets on the very next orbit and came down in the Pacific, far from the planned recovery zone. Once again, rescue forces scrambled to find a small capsule bobbing in a big ocean. When they did, they pulled out 2 astronauts whose expressions in photographs look less like exhilaration and more like the sober afterglow of people who know they have just survived something that could easily have gone the other way. Investigations traced the stuck thruster to an electrical fault. Procedures were changed, hardware was redesigned to allow isolation of a failed jet more quickly. The episode also left a deep impression on the people deciding who should command the first lunar landing. Here was a pilot who had faced a nearly unrecoverable situation in orbit, with his spacecraft tumbling and the ground far away, and had still found a path to stability. That kind of composure was going to matter on machines yet to be built. Other Gemini flights continued to extend the ladder upward. Gemini 10 and 11 tested rendezvous with multiple targets and used the docked stage's engine to climb to higher orbits, simulating parts of the velocity changes needed for lunar missions. Gemini 12, flown by Jim Lovell and Buzz Aldrin, refined spacewalk procedures with better handholds and more realistic work tasks, drawing on Aldrin's doctoral research on orbital rendezvous and extravehicular activity. Each mission turned once theoretical ideas into muscle memory and checklists. By the time the last Gemini capsule splashed down, human spaceflight had changed its character. It was no longer a sequence of one-shot demonstrations. It was starting to look like an operational craft and a set of practices that could be built upon. Astronauts had spent nearly 2 weeks in orbit without falling apart. They had walked and worked outside their ships. They had chased down and docked with targets. They had handled unexpected events, from stubborn hatches to terrifying spins, and brought their machines and their bodies home. From the outside, the public saw a string of missions with memorable numbers and a handful of dramatic headlines. From the inside, engineers and mission planners saw something else. They saw a proof of concept that lunar orbit rendezvous was not science fiction, that crews could handle the isolation and stress of longer journeys, and that the combination of human judgment and machine reliability could be balanced in a way that gave each its proper place. The stage was set for a new kind of rocket, vastly larger than Titan, and a new set of missions that would leave Earth orbit entirely. Yet for all the check marks in the success column, the path ahead was not smooth. The hardware for the next step would have to be bigger, more complex, and more tightly integrated than anything flown before. The stakes would move from laboratory-level risk into something closer to national myth. And before anyone could plant a boot in lunar dust or swing a golf club in low gravity, there would be a night on a launch pad in Florida when fire took 3 lives and forced everyone involved to ask how far they were really willing to go. The night of the fire began like a rehearsal, a test on the pad, not a launch. Gus Grissom, Ed White, and Roger Chaffee climbed into the Apollo command module, perched on top of a Saturn rocket at Cape Kennedy, sealed the hatch, and prepared for what was supposed to be a routine plugs-out test. No propellants loaded in the big stages, no countdown to ignition, just a check that the spacecraft could run on its own power and respond to simulated commands. Outside, the wind blew across the pad, and technicians watched instruments. Inside the cabin, the atmosphere was pure oxygen at high pressure, a choice made for simplicity that turned the interior into a tinderbox. The first hints of trouble were small. Voice loops picked up complaints about a smell in the air, a sour note in the life support system. Communications were scratchy, lines were busy. There was no sense of immediate danger until a sudden shout came through the audio that spoke of fire. The oxygen-rich air turned a small spark into an inferno in seconds. Flames raced across insulation and straps. Temperatures soared. The crew tried to fight the hatch, but the pressure inside the cabin had risen, jamming it shut. Outside, rescuers battled smoke and heat, beating on the door that would not open in time. By the time the hatch was forced, all 3 men were gone. The fire had consumed the cabin atmosphere and left behind charred wiring and blackened panels. For the program, It was a moment of brutal clarity. The rush to put a man on the moon had collided with basic safety. Small design decisions that seemed acceptable in isolation had combined into a lethal trap, would have to be rebuilt from the inside out. Investigations traced the fire to a likely spark in frayed wiring near a footrest, but the deeper conclusions were broader. The cabin atmosphere needed to be changed, the materials inside made less flammable, the wiring rerouted and protected, the hatch redesigned so that it could be opened quickly from the inside, even against pressure differences. Astronauts who had once joked about flying dangerous machines without complaint now sat on review boards and demanded changes. Engineers tore into their own work, looking for weak points they had been too hurried or too proud to see. In a strange way, the fire may have saved later crews. By stopping the program before its first manned flight, it forced a reckoning that might not have happened until a disaster in deep space, where rescue would have been impossible. When Apollo flights resumed, they did so with a spacecraft that had been burned down to its fundamentals and rebuilt with safety much more prominent in every trade-off. The cost had been 3 lives and a national shock. The question hanging over everything was whether the promise made earlier in the decade still held. That promise had been made in a speech in 1961, when President John Kennedy stood before Congress and the nation and declared that the United States should commit to landing a man on the moon and returning him safely to Earth before the end of the decade. At the time, that sentence was closer to science fiction than policy. The country had only just put a person on a brief suborbital flight. The idea of designing a giant rocket, a lunar lander, navigation systems and procedures in less than 10 years was audacious, bordering on reckless. Behind the scenes, engineers argued about how to do it. One school favoured direct ascent, a single massive rocket blasting off from Earth, flying straight to the lunar surface with a lander attached, and then climbing directly back. Another group argued for Earth orbit rendezvous, where pieces would be assembled in orbit. A third idea, championed by a relatively unknown engineer named John Hobart, proposed something stranger. He suggested that a single Saturn rocket could launch a combined command ship and lander, that they would separate in lunar orbit, with only the small lander descending to the surface. After the exploration, the upper part of the lander would lift off and dock again with the mothership. Lunar orbit rendezvous sounded complex and risky to many. The notion of 2 spacecraft playing docking games around another world made some planners nervous. Yet when they ran the numbers, it became clear that this approach allowed a more manageable rocket and a more focused lander. Hobart fought passionately for his concept, writing letters and making presentations that sometimes angered superiors. Eventually his logic won. The Apollo architecture would revolve around a command and service module that never touched the moon, and a separate lunar module that would be the actual legs and cabin on the surface. With the concept chosen, the hardware had to be real. The Saturn V rocket that emerged from drawing boards and test stands was unlike anything that had flown before. Taller than a skyscraper, with 3 stages stacked like a totem of steel and propellant, it was a controlled explosion designed to push a payload of tens of thousands of kilograms beyond Earth orbit. Standing near it on the pad, you would feel small in a way that no photograph can fully capture. Each of its first stage engines could lift an ocean-going ship. Together they formed a cluster that had to ignite in near-perfect unison. The first unmanned test flights of Saturn V revealed their own problems. One mission suffered violent vibrations in the second stage that threatened to tear the structure apart. Engineers traced the effect, called pogo, to feedback between engine thrust and fuel flow. They added dampers and modified systems to tame the oscillations. In another flight, some engines shut down early, forcing the upper stages to work harder to reach orbit. Each issue was a reminder that this was no longer the world of small experimental rockets. The energies involved here was so large that mistakes could be catastrophic, on a scale that made even seasoned test pilots uneasy. While hardware matured, the geopolitical context sharpened. The moon race had become a proxy for deeper ideological competition between superpowers. Each success was trumpeted as proof of system superiority. Each failure was downplayed or wrapped in secrecy. For ordinary people, a more personal, emotional thread ran alongside. The moon was not an abstract target. It was a familiar presence in the night sky, the subject of myths and lovers' songs. The idea that humans might actually walk on its surface within their lifetime felt both thrilling and faintly sacrilegious. The first crewed Apollo missions after the fire stayed close to home, flying in Earth orbit to test the redesigned command module. Apollo 7 checked life support, navigation, and docking operations with a dummy lunar module. It was an essential but somewhat unspectacular flight. The real psychological leap came with Apollo 8. This mission would send a crewed spacecraft all the way to lunar orbit for the first time, without a lander, purely to test navigation, communication, and the deep space environment. For Frank Borman, Jim Lovell, and Bill Anders, it meant being the first humans to leave Earth orbit entirely. When their Saturn V lifted off in December 1968, the world below was in turmoil. Protests, assassinations, and war had marked the year as one of the most turbulent in living memory. Against that backdrop, 3 men disappeared into the sky on a controlled pillar of fire, rode for hours through the void, and then fell into the gravitational grip of another body. As they slipped behind the moon, radio contact cut out, a planned silence that still felt eerie. When they emerged and pointed a camera back toward Earth, they captured an image that would become iconic. The photograph, known as Earthrise, shows our planet as a small blue and white marble emerging above the grey horizon of the moon. Borman and Anders later described how seeing it out the window shifted their sense of scale. From lunar orbit, national borders vanish, storm systems swirl, the whole of known human history floats as a fragile globe in a vast black sea. For many viewers back home, that image did something similar. It reframed the space race from a contest to plant flags into a wider reflection on our shared home. Technically, Apollo 8 proved that navigation to lunar orbit and back was possible, that communication could be maintained at that distance, and that crews could handle the psychological stress of being far from Earth with no immediate way back. Emotionally, it set the stage for the next step. The question was no longer whether humans could orbit the moon. It was whether they could descend, land, walk, work, and come home again. The machine that would make that attempt possible looked nothing like a sleek rocket or an aircraft. The lunar module was a spidery, angular craft with thin walls and insect-like legs. Designers had freed themselves from aerodynamic constraints since it would never fly through air. Instead, it was shaped only by function. Its descent stage carried a large engine, fuel, and landing gear. Its ascent stage was a small cabin with windows, controls, and another engine to climb back to orbit. The metal between the inside and the vacuum outside was in some places thinner than a coin. Astronauts joked that they were flying inside gold foil, and they were only partly exaggerating. Apollo 10 took the lunar module down close to the surface as a full dress rehearsal, skimming above craters and rocks before firing its engine to climb back. The first true landing attempt came with Apollo 11. The crew consisted of Neil Armstrong, Buzz Aldrin, and Michael Collins. Armstrong and Aldrin would ride the lunar module down. Collins would stay in the command module above, essentially becoming the loneliest person in the solar system for a few hours, orbiting a world with all of humanity gathered on its far side. The descent to the moon on that mission did not go exactly as planned. Computer alarms triggered partway down, caused by overloaded processing units juggling radar data and control commands. Controllers on the ground, who had seen those warnings in simulations, decided they could be ignored. As the module dropped lower, Armstrong saw that the programmed landing zone was littered with boulders. He took manual control, using the remaining fuel to guide the craft to a flatter spot. Fuel indicators dipped toward critical levels. When the legs finally touched dust and the engine shut off, the margin left was measured in seconds. People remember the first steps and the words spoken as Armstrong climbed down the ladder and placed his boot in the powder. What is easy to forget is how much of that first excursion was work. Aldrin and Armstrong deployed experiments, collected rock samples, and took photographs while watching their oxygen and time. The suits were bulky, the gloves stiff, their breath frosting the inside of the visors. Moving in low gravity took practice. Jumps that looked graceful in training videos sometimes turned into awkward hops as their bodies learned new rhythms. Back on Earth, hundreds of millions watched grainy television images and listened to crackly audio. For a brief window, the moon race felt like a completed story. Plant the flag, say the lines, bring the crew home, roll the credits. Yet the program continued. Apollo 12 landed more precisely near a robotic surveyor to study how materials had fared on the surface. Apollo 13 suffered a crippling explosion en route, forcing the crew to use the lunar module as a lifeboat and slingshot around the moon without landing. Their survival turned into its own saga of improvisation and teamwork. By the time Apollo 14 flew, the mission template was well established, but the novelty had faded a little in the public mind. The moon landings were still extraordinary, but they were beginning to feel less like unique miracles and more like a series. Networks cut away earlier from coverage. Newspaper front pages gave space to other stories. It was in this context that an astronaut quietly decided to smuggle a small symbol of normal leisure into the most alien environment humans had ever visited. Alan Shepard, the same astronaut who had made America's first suborbital flight years earlier, now commanded Apollo 14. Tucked away in his personal items was the head of a golf club that could be attached to a tool handle and a couple of balls. He had cleared the stunt in a limited way with some managers, framing it as a light moment, but it was not part of any official experiment. After finishing the more serious tasks on the lunar surface, he produced the makeshift club, dropped a ball onto the dust, and took a swing. In Earth gravity, a golf swing is a familiar arc, constrained by weight and air resistance. On the moon, with weaker gravity and no air, the ball's flight becomes something stranger. Shepard topped the first attempts, sending the ball bouncing and skidding. Then he connected cleanly. The ball sailed off in a slow, graceful trajectory, arcing across the stark landscape until it became a tiny speck and vanished from view. In later retellings, he joked that it travelled for kilometres. The actual distance was more modest, but the point was never about measurement. What matters about that swing is what it says about how quickly humans turn even the most extreme frontier into a place where play is possible. A world that for ancient storytellers had been the realm of gods and spirits, had within a few missions become a place where a person could pause between scientific tasks to hit a ball for the simple joy of seeing it fly. There is something charming in that, and also something slightly unsettling. It hints at how easily we can normalize almost anything once we have done it a few times. After Apollo 14, there were a few more landings, each adding to the haul of rocks and the list of experiments. Apollo 15 took a small rover, allowing longer excursions. Apollo 16 and 17 explored different terrains. Yet the political and financial winds were already shifting. The cost of the program was enormous. Other priorities at home and abroad were clamoring for attention. Plans for extended lunar bases and follow-on missions were scaled back or shelved. The last crew left the moon in 1972, climbed the ladder and blasted off, leaving behind footprints, rover tracks, and a few scattered artifacts, including those golf balls slowly half-buried in dust. In the decades since, no human has returned to that surface. The moon landings remain a moment when human presence briefly leaped from one world to another and then retreated. The knowledge gained has shaped geology, planetary science, and our understanding of how the Earth and Moon formed. The images and stories have shaped art, politics, and personal dreams. Yet there is a sense of incompleteness, a feeling that we opened a door and then closed it again before really looking around. While the last Apollo missions were still being planned, some people were already thinking about a different kind of exploration. If you want to see what lies beyond the orbit of the Moon, the distances and conditions become inhospitable to human bodies very quickly. Radiation increases, travel times stretch to years, life support becomes a heavy burden to carry. The obvious answer is to send machines in our place, small and durable, with cameras for eyes and instruments for fingers. In the 70s, a pair of such machines would ride their own columns of fire away from Earth and begin a journey that would turn the outer planets from faint dots into detailed worlds. and eventually carry our presence all the way into the space between the stars. In the 1970s, when people were still getting used to the idea that footprints on the moon were real and not a dream, a small group of engineers and scientists sat down with a different kind of ambition. Instead of asking how to send a person somewhere, they asked how to send curiosity itself. They wanted machines that could look where human eyes could not yet survive, and keep reporting back long after any normal mission would have died. They knew that the outer planets were lining up in a rare pattern that would not repeat for more than a century. If they could launch at just the right moment, a single spacecraft could fall from one gravity field to another in a kind of cosmic slingshot and tour the whole outer system. The idea was as bold in its own way as landing on the moon. To work, these machines would have to fly for more than a decade, crossing billions of kilometers through a vacuum full of radiation and dust. They would need to wake themselves up on schedule, point their instruments with precision, and fire small thrusters that could not be serviced or repaired. Every radio call would take hours to cross the distance, so there would be no quick joystick corrections from Earth. Once a course correction was sent, engineers could only wait and hope that the craft had understood. 2 spacecraft took shape on the assembly floors, twins in design but destined for different paths. They were named Voyager 2 and Voyager 1, in that order, because the first to launch would actually follow the slightly longer, slower route. Each Voyager was about the size of a small car, with a wide dish antenna like a white shield, and a forest of booms and sensors sprouting from its body. 3 nuclear power units hung on one side like small barrels, warm to the touch, ready to convert the heat of radioactive decay into electricity. Where earlier probes like Pioneer had been scouts, these were meant to be full surveyors. In August 1977, Voyager 2 rode a Titan Centaur rocket into the sky from Cape Canaveral. A few weeks later, Voyager 1 followed. Once free of the last wisps of atmosphere, each spacecraft unfolded its magnetometer boom, oriented its dish toward Earth, and began to take the first of what would become hundreds of thousands of measurements. Their initial paths were not yet spectacular. For months they cruised through the inner solar system, crossing the orbits of Mars and the asteroid belt, little more than faint artificial stars, guided by bursts of chemical flame. The first real drama came as they approached Jupiter. From Earth, Jupiter is a bright point, sometimes a tiny disk through a backyard telescope. To the Voyagers, it grew from a pale sphere into a looming world wrapped in swirling clouds. They photographed the Great Red Spot, a storm larger than Earth that had raged for centuries, and saw it in motion, bands of gas flowing around it in complex spirals. They captured lightning in the Jovian atmosphere and revealed faint rings that had been invisible from home. The planet suddenly felt less like a symbol on a chart and more like a living weather system. Perhaps the most startling discoveries were not about Jupiter itself, but about its moons. Voyager images showed Io as a tortured yellow world covered in sulfur-rich plains and dark scars. Careful analysis revealed active volcanoes blasting material high into space, the first time anyone had seen eruptions on another body. Europa, another moon, appeared smooth and bright, its surface crisscrossed with delicate brown lines. The patterns looked like fractures in a thick shell of ice, hinting at a liquid ocean below. Ganymede and Callisto, long thought of as simple points of light, became cratered and layered landscapes. Each new picture rewired assumptions. Worlds that had been background actors in planetary diagrams suddenly took on character and complexity. You can imagine a planetary scientist sitting in a darkened room at the Jet Propulsion Laboratory, watching new frames appear on a monitor, leaning forward as if they were looking out a porthole. For months, the Voyagers flew through that system of giants, trading data for propellant as they used Jupiter's gravity to bend their paths onward. When they finally left its influence, they carried with them more questions than answers. Saturn waited farther out, pale and elegant. When the Voyagers reached it, the planet's rings, once seen as smooth bands, exploded into fine structure. The spacecraft cameras and instruments traced wave patterns in the rings that echoed the gravitational tugs of moons, like musical notes plucked on a vast disk of ice and rock. Gaps, twists and braids appeared, each a clue to an ongoing dance of particles. Saturn itself showed banded clouds and fierce storms, but it was the rings that grabbed the imagination. They turned from a textbook icon into a dynamic system barely held together by balance and chance. Saturn also had a moon that called for special attention. Titan, wrapped in a thick orange haze, refused to reveal its surface to visible light. Instruments on the Voyagers probed its atmosphere instead and found organic molecules, nitrogen-rich air, and conditions that felt hauntingly reminiscent of a very early Earth, though far colder. There was no way to see lakes or rivers through the haze then, but Titan's stubborn secrecy planted seeds for future missions that would eventually land there. For Voyager 1, however, the encounter with Titan was a fork in the road. To fly close enough to Titan to gather useful data, Voyager 1 had to bend its path sharply. That turn stole the energy it would have used to continue on to Uranus and Neptune. Its route tipped upward out of the plane of the planets, putting it on a trajectory that would eventually carry it out of the solar system entirely. Voyager 2, which met Saturn later on a slightly different path, kept the option open. It skimmed past the ringed planet, gathered its own trove of images and fields data, and then fell outward again, headed for worlds no probe had yet visited. Uranus was, to most of the world, a punchline before Voyager 2 arrived. From telescopes, it was a faint blue-green disk, tilted strangely on its side. When the spacecraft reached it in 1986, Uranus became a real place. Its atmosphere showed bands and a few delicate storms. Its rings, dark and narrow, glowed faintly. Its moons displayed icy cliffs, canyons, and puzzling dark and bright patches. One moon, Miranda, looked almost like a collage, with pieces of terrain stitched together at odd angles, as if some ancient violence had shattered and reassembled it. Neptune lay still farther in the dark, a cold giant at the edge. Voyager 2's path intersected it in 1989. Again, a planet that had been a blurry orb turned into a dynamic world. Neptune's atmosphere held a swift spinning storm that observers dubbed the Great Dark Spot, clouds racing around the planet in some of the fastest winds ever measured. Its largest moon, Triton, showed plumes shooting icy material from its surface, another example of active geology in a place where no one had expected it. After this final close encounter, Voyager 2, like its sibling, headed outward along a path that would never loop back. If you map their journeys, the two spacecraft trace spirals and arcs that look delicate on a page, but represent distances the human mind struggles to picture. Each new planetary flyby had to be planned years in advance. A small engine burn at the right point could change an arrival time by hours and a closest approach distance by thousands of kilometers. There was no second try. The window for a gravity assist at each planet was unforgiving. When the Voyagers nailed those windows again and again, it revealed not just their clever design, but the quiet miracle of the underlying celestial mechanics we had worked so hard to understand. All the while, their radio signals grew fainter. Each Voyager's powerful antenna on Earth had to listen for whispers against background noise, like trying to hear a watch ticking on the other side of a continent. Data rates dropped as the distance increased. Images that had once streamed back quickly now took long minutes to assemble, line by line. Engineers nursed power budgets, shutting down non-essential instruments, reprogramming computers that had less memory than a modern phone, stretching every watt. The fact that they could send new commands at all, decades after launch, was itself a kind of quiet wonder. Long before they reached the boundary of the Sun's influence, the Voyagers had already done more science than their designers had formerly promised. Yet the teams behind them had one more set of ambitions, this time not purely scientific. They wanted these machines to carry something of us, not just as engineers but as a species. Under the guidance of astronomer Carl Sagan and a small committee, each Voyager was fitted with a golden phonograph record, sealed against dust, bolted to the side like a strange, shining plaque. On those records were encoded sounds and images from Earth, greetings spoken in many languages, a heartbeat, laughter, music from different cultures, photographs of landscapes, cities, animals, and people. Simple diagrams that explained how to play the record, pointed to the location of our sun relative to certain pulsars, and gave basic information about the chemistry of our bodies. The record was not meant for us. It was a message in a bottle, intended for any future intelligence that might find the probe drifting in the dark, long after humans were gone or unrecognizable. The odds that anyone will ever pick up those bottles are tiny. Space is vast, and the probes are small. Yet the act of sending them carries its own meaning. It says that we were here, that we tried to understand, that we wanted to be known. In a way, it closes a loop that began when astronomers first named planets after gods and hoped that their discoveries would outlive them. Vulcan never existed, but the desire behind it, the urge to leave a mark beyond the atmosphere, now rode out of the solar system, stamped into metal and grooves. As the Voyagers left the orbits of the planets behind, they entered a region where the sun's influence fades into the background of the galaxy. The solar wind, a stream of charged particles blowing outward from our star, eventually meets the thin gas between the stars and slows. Somewhere in that transition zone lies the heliopause, the boundary between our local bubble and interstellar space. Instruments on the spacecraft watched as the flow of particles changed, as cosmic rays from the wider galaxy increased, as magnetic fields shifted direction. Voyager 1 crossed that boundary first, according to most measurements, entering interstellar space in the early 21st century. Voyager 2 followed years later along its own path. There is still debate about the exact location and shape of the heliopause, but what matters for the story is this. For the first time, machines built by human hands moved from being objects in the solar system to being objects in the space between stars. They carry with them local measurements of density, radiation, and fields that no other sensor has ever touched. Before they reached that point, however, one of the spacecraft performed an act that may be their most powerful legacy, and it did not involve any new planet at all. In 1990, engineers commanded Voyager 1 to turn its camera back toward home from a distance of about 6 billion kilometers. The resulting image, later known by a now famous phrase about a pale blue point, shows Earth as a tiny speck caught in a beam of scattered sunlight, almost lost in the noise. No continents, no clouds, no visible sign that the dot is anything special. Carl Sagan, who had lobbied for that image, later wrote and spoke about what it meant to him. He pointed out that on that small point, suspended in a sunbeam, every person who had ever lived had played out their dramas. Every general, every king, every teacher, every child. He asked listeners to think about the rivers of blood spilled by those who wanted to be temporary masters of a fraction of a dot. He urged a sense of responsibility for this tiny world, the only home we have known, and for the thin film of life that covers it. You do not have to agree with every line of that reflection to feel its weight. The photograph compresses all our stories about importance and power into a single pixel that could vanish with a smudge of dust on the lens. When you look at it, arguments about who owns what piece of land, or which nation is ahead in which race feel smaller, not because they are unimportant to people, but because they are nested inside something larger. The same longings that pushed Leverrier to chase planets and drove governments to build rockets also pushed us to take that humbling look back. In a sense, the Voyagers are the opposite of Prospero. That small British satellite circles close to Earth, a relic of a choice to stop. Voyagers 1 and 2 head out, silent ambassadors of a choice to continue. Ham the chimpanzee flew for minutes at the very edge of space, terrified and unknowing. The Voyagers fly for decades in a state beyond fear, because they have no minds to feel it. Yet all of these stories are tied together by the same thread. They are experiments in how far we can stretch ourselves, in how much we are willing to risk or abandon in order to learn. Remember the first part of this journey, when a planet that never existed fooled proud astronomers. That mistake taught us that the universe will not bend to our hopes. The correction that followed, the rise of general relativity, allowed us to plot trajectories with enough precision that a probe launched in the 1970s could hit a moving target near Neptune many years later. The path from a ghost planet inside Mercury's orbit to detailed images of storms on distant worlds is not straight, but it is real. Each misstep, each cancellation, each near disaster leaves residue. Sometimes that residue is painful memory, like the fire that reshaped Apollo. Sometimes it is hardware in orbit, like Prospero. Sometimes it is a pattern of equations on a blackboard that makes better sense of the sky. The Voyagers are not just machines, they are crystallized patience. They embody the idea that if you keep refining questions and tools across generations, you can eventually send a camera to places your grandparents could not even imagine visiting in dreams. Their power supplies are fading. Instrument after instrument will go dark over the coming years to conserve the last trickle of energy. At some point, they will fall silent completely, no longer able to send whispers across the dark. They will not stop moving. They will continue along their paths for millions of years, looping once around the center of the galaxy and then again, long after the languages engraved on their records have changed or vanished. In that distant future, they will be tiny, cold artifacts, bearing the fingerprints of a species that, for a brief time, looked up and decided to reach. When you think of them that way, a strange feeling arises. On the one hand, their journeys make our individual lives seem even smaller than Mercury's arc around the Sun. On the other hand, they show that being small does not mean being powerless. A quiet mind working on the mismatch in an orbit can change the way we model gravity. A relatively poor country can, for a moment, launch its own satellite and prove that capability is not limited to empires. A chimp, frightened and alone in a metal shell, can help pave the way for people to see their planet from above. Perhaps that is the real gift of these stories. They do not flatter us with the idea that we are central or destined to rule. Instead, they invite us into a more honest and, in a way, more beautiful role. We are the part of the universe that has started to notice itself, to track its own shadows, to send pieces of itself outward as questions. Whether or not anyone ever finds the golden records, the act of making them says we were willing to speak beyond ourselves. Somewhere, far outside the orbit of Neptune, two small spacecraft continue to drift. Their dishes stay aimed as best they can at a pale point of light that once filled their cameras and now is just a direction. On that point, people still argue about budgets and borders, still tell stories about heroes and villains, still look up at the night sky and feel something that is hard to name. Curiosity, fear, wonder, the need to be remembered, the need to understand. All of that is packed into the faint radio signals that occasionally brush past the vast empty spaces and arrive, hours later, at a handful of antennas on a small, spinning world. If you ever feel tempted to think that nothing you do matters against the backdrop of galaxies, remember this. Every equation corrected, every mission debated, every risk accepted or rejected nudges the path of our future experiments. Sometimes that leads to chasing ghosts like Vulcan. Sometimes it leads to real planets and real storms and real oceans of ice under alien skies. And sometimes, if we are careful and a little lucky, it sends a small machine out into the dark, carrying, in its circuitry and its grooves, the simple message that we were here and we were paying attention.